Okay, so we're going to look at another strategy that makes integrating very helpful. So if we want to look at this integral here that I have set up at the top, we can see pretty quickly that any of the strategies we have so far are not going to work. If we think about using u substitution, we would need u to be x squared minus 7x plus 12. That would make du equal to 2x minus 7 dx. That's not going to be something that we're able to get out of there. Completing the square might be an option. It doesn't look super user-friendly at this point because of the value of b that we have, and I don't know that it would even get us to what we want in the first place. So that means that none of those strategies are going to work, and we need to try something else. So this is a great one for partial fraction decomposition. Now, just so you know, there is another way that you can do this if this is something you want to look at on your own, and that is called trigonometric substitution. That's not part of the BC curriculum. That's not something that we work on in this class because it does take quite a bit of time. So instead, if we knew that 1 over x squared minus 7x plus 12 dx breaks down to the integral of negative 1 over x minus 3 plus 1 over x minus 4, then we can do this pretty simply. Those are both going to be natural logs when we take the integral there. But where do we pull those fractions out of? You can see going backwards, if you find a common denominator there, you're going to end up with 1 over x squared minus 7x plus 12. But how do we do this in reverse? So this is a strategy that's called partial fraction decomposition. We're trying to take one fraction and break it into parts of partial fractions that don't necessarily have the same denominator. So the first thing, this is sort of your checklist as you attempt partial fractions. The first thing is that if the degree of the numerator is greater or equal to the degree of the denominator, we want to divide. You want to use long division or synthetic division when it's possible. Remember, that has to be a linear factor with a coefficient of 1. It has to be in the form of x minus c. To simplify that way, that's always going to be pretty quick. So you always want to start there first. Partial fractions doesn't work if the numerator has a greater degree than the denominator. So that's the first thing we have to take care of. Then we want to factor the denominator because typically that's going to show us what our denominators were before we combined. Completely factor the denominator into linear and quadratic factors. This is something you practiced a lot in pre-calc, getting it factored completely into linear and quadratic factors. Then here is how you're going to set up the partial fractions, and I'm going to just kind of let you take a second to look at this, and then we'll see a little bit more in action. This makes a little bit more sense. Just note that when they are linear factors, you are going to have a single constant value on top, a1, a2, up through whatever, am in this case. And so that is what that will look like. If those factors are squared, or I should say any power bigger than 1, let's say that I had a factor of x plus 1 to the third, I would need a fraction that had x plus 1, plus another fraction that had x plus 1 squared, plus another fraction that had x plus 1 cubed in the denominator. Then you're going to do similarly for each quadratic factor, but the numerators look different. Those are going to be bx plus c looking numerators. And that's something that we'll work on in our next lesson. So I know that this is kind of hard to visualize what we're doing just yet. So let's look at this one. This is the one that we've been talking about. We want the partial fraction decomposition of 1 over x squared minus 7x plus 12. So the first thing that we do is we factor. So that is going to look like 1 over x minus 3 x minus 4. That's the factored form there. Now, when we do that, there's a little bit of lag on this video, I think. My internet's being really slow. I apologize. We're going to break that up. Since those factors are both linear, we're going to have a single constant in the denominator, but we don't know that they're the same. So we're going to start with a over x minus 3. That's our first one. Plus a different constant, b, over x minus 4. Now, what we want to do is we want to eliminate those denominators. So we're going to multiply through by the LCM. So in this case, we're going to multiply both sides by x minus 3, x minus 4. Oops, we want all the denominators gone. Okay, that cancels both of them out on this side, so we're just left with 1. With the a, the x minus 3's divide out, so we have a times x minus 4. Plus, in this case, the x minus 4's divide out, so we get b times x minus 3. Now, here's where this seems like you shouldn't be able to do this, but you can. We are simply going to choose convenient values for x. We are going to try to solve for a and for b. And so we just want to pick numbers that are going to be easy to substitute here. So we want to choose convenient values for x. What would make them convenient is that they're going to either eliminate a or b. Okay. So, for example, I'm going to come over here and I'm going to say let x equal 3. Because when I let x equal 3, that makes it a times x minus 4 plus b times 0. That means that I'm left with the equation 1 equals a times 3 minus 4. Because again, we plugged in 3 for x. That canceled out the b term, but in the a term, I still have to subtract that out. So I get 1 equals negative 1a. So that means that a is going to be negative 1. So we're going to use that value for a. And it seems weird that you can pick anything you want, but we can because it's a proportional relationship between a and b here, the way that we've got this set up. This is a balanced equation. So as long as you plug in anything, it should end up staying consistent between the two. So now I'm going to choose to let x equal 4. Because that's going to eliminate a this time, and I need to figure out what b is. So if I let x equal 4, that means I get 1 equals 1b, and there's that already. Now I know that b is equal to 1. That tells me then that my partial fraction for this equation is going to be, a was negative 1, so that's going to be negative 1 over x minus 3, plus b, which was positive 1 over x minus 4. That's how we obtain that partial fraction decomposition there. Okay? Then if we want to integrate that, it becomes really simple. Let's look at another one. Okay, so this one is very similar. This is going to be another one that has distinct linear factors, meaning they're different. Okay, so here's another one. We are going to start by factoring the denominator. So we will start by rewriting this. This is going to be, our numerator is 1 again. That's nice. Over x squared minus 5x plus 6 is going to factor 2x minus 2 and x minus 3. So we write that as two separate fractions with unknown numerators. So this is going to be a over x minus 2 plus b over x minus 3. If we multiply through by the LCM, that tells us that we have the following relationship. We're going to multiply by the denominator of the initial fraction. That's what it's going to be every time. So we're going to get 1 equals a times x minus 3 plus b times x minus 2. Now again, I kind of skipped a step here, but what we did was multiply everything through by x minus 2, x minus 3. Okay, this is where we get to choose values that we like. So I'm going to let x equal 3. When that is the case, I get 1 equals a times 0 equals b times 3 minus 2, which is 1. So 1 equals b. It doesn't always work out this way, but that's what we've seen so far. Now, if I choose to let x equal 2, then that means I get 1 is equal to negative 1a. So a is equal to negative 1. Now, the only reason that it's happening this way is because both of the examples we've seen had numerators equal to 1. And there was no like GCF or anything in the denominator. It's not always going to be 1 and negative 1, so I don't want you to overgeneralize there. So the partial fraction decomposition then is going to be a was negative 1, so negative 1 over x minus 2 plus b, which was 1 over x minus 3. So again, all we're doing is kind of working backwards from our common denominator to figure out what the uncommon denominator would have been. So let's look at one more where we're not necessarily going to get 1 and negative 1, and let's put this into the case where we have we want to actually do the integral. Sorry. So there's also a typo here. There should be a plus between that x cubed and the 2x squared. This should say plus here, x cubed plus 2x squared plus x. So we're not going to do anything with the numerator. We're only concerned with what the denominator is going to do, okay? So this makes our substituting a little bit trickier, but that's the only thing that it does. First thing we need to do is factor the denominator. So we're going to leave the numerator alone. 5x squared plus 20x plus 6 over. We can definitely factor out an x, and then that leaves us with x squared plus 2x plus 1, so that's in a perfect square, x plus 1 squared. Now, this is where we have a repeated factor. So we are going to have to break this apart into 3 things. We have one linear factor that is x, so we're going to have a over x plus. We have x plus 1 is another linear factor. So there's the case that I only have one of them, x plus 1. Then there's the third case, or well, the second case of this one, but that I had my factor of x plus 1 squared. So if that was, like I mentioned before, if that was x plus 1 to the 5th, we would need a factor for x plus 1 squared, x plus 1 cubed, x plus 1 to the 4th, and so on, up to x plus 1 to the 5th. We'd have to have an a, b, c, d, e, f, all the way up. Okay, now we multiply through. Again, we're going to multiply everything by that denominator in its factored form. So x times x plus 1 squared, that's what we multiply by. That should leave us with only the numerator on this side. That's our goal. So we have 5x squared plus 20x. 20x plus 6 equals, let me close this down, hold on. Okay, so the x is going to cancel, and I'm left with a times x plus 1 squared. Then I have plus b x plus 1 plus c x. That's what we get when we multiply all of that through. So now again, we are going to choose convenient values for x. anything that is going to work out nicely for us. So I'm going to let x equal -1 to start, because that's going to take care of any of these factors that have an x plus 1 in them. So if x is equal to -1, now here's what we can't forget, is that we have x's on this side now, which we didn't before. So we get 5 times -1 squared plus 20 times -1 plus 6 equals, the first one zeroes out, the second one zeroes out, and we just get -c. So when we work all of that out, we get -9 equals -c. So c is equal to 9. Got one. Now let's choose another value for x that is convenient. So I'm going to choose to let x equal 0. That's going to take care of any of the terms that have just an x in them. So that's kind of easy to plug in on the left. We get 0 plus 0 plus 6. So that is 6 equals, we're going to have a times 1 squared. So that's just a, plus b times 0, that's out, plus c times 0, that's out. So now I have a and I have c. The problem at this point is that we're kind of out of convenient values. Convenient in the sense that they're going to cancel out one of our factors. We don't have any more of those. So let's just pick a number that's nice. We could use any x we want. I'm going to choose 1 because that's an easy number to substitute. And then we're going to use the fact that we've already determined that a is 6 and c is 9. So now, using this information and choosing to use a simple value of x equals 1, I get, if we plug in 1, we get 5 times 1 plus 20 times 1 plus 6. That comes out to 31. That's from substituting in on the left side of the equal sign. And that equals, we're going to let a be 6. And then this is going to be 1 plus 1, so times 2 squared, plus b times x, which is just 1, that's what we chose, times 1 plus 1, which is 2. B is the one we don't know yet. And then we have plus c, which we decided was 9, times x, which is 1. That comes out to 31 equals 33 plus 2b. So if you subtract 33 and divide by 2, we can see that we get -1 for b. Okay, so what does that do for us? Well, don't forget, we're trying to find an integral here. So now we need to set up our integral, and we're nearly done because once we do this, this is all pretty simple. So we want the antiderivative of a over x. Well, we determined a to be 6. So this is 6 over x plus b, which we got to be -1 over x plus 1 plus c, which is 9 over x plus 1 squared dx. Okay, now we can go through term by term and integrate that expression. So the first one is just 6 over x. Well, that's 6 times 1 over x. So that's going to be 6 times the natural log of the absolute value of x. The next one is going to be very similar. That's going to be minus the natural log of the absolute value of x plus 1. Technically, you're using u substitution there, but when you take the derivative of x plus 1, you just get that du is equal to dx. So you can kind of figure that one out without having to write it out too much. Now, for the for the third one, we do have to think about this in a little bit more detail here. If we let u be x plus 1, then du is dx, just like it would have been before. But so what we're really doing is 9 times the antiderivative of u to the -2 du, which is going to come out to be -9 over u. So we can figure out then that our last one is minus 9 over x plus 1. And then don't forget your plus c, because that was all part of one integral. And so there it is. That, I think, is a pretty neat strategy to be able to break that apart and do something that we wouldn't have been able to integrate any other way. U substitution definitely wouldn't have worked here. Integration by parts wouldn't have worked. None of our strategies so far would work. So this is kind of a neat way to break it down with some pretty simple algebra. So we will look at quadratic factors the next time. So I will see you all soon.